In this video, we're going to prove that in a principal ideal domain, irreducibles are prime. In a previous video, we talked about the definitions of irreducible versus prime, and we talked about how they're not the same definition, but they are related. And we also showed in a previous video that in any integral domain, every prime is irreducible. In this video, we're going to show that under certain circumstances, the converse is true, that irreducibles are always prime. But we need a principal ideal domain to be able to say that. So first of all, just for motivation and also connection to other content that you might be familiar with, let's just recall in number theory, where we're interested mostly in the integers, the way that we defined prime number was we said P is a prime if P was greater than 0. We usually only refer to positive integers as being prime in number theory, although you can always define prime to include negative integers as well. But typically we mean P is greater than 0 and P is not equal to plus or minus 1. And if P is equal to A times B, then either, this is assuming, by the way, that A and B are also greater than 0, then either A is equal to P and B is equal to 1, or A is equal to 1 and B is equal to P. That's the definition of prime, and it's a little bit more contrived than what we've been working with, because in number theory we don't usually bother building all of this infrastructure around irreducibles and primes and ideals and all of that, so the definition looks a little bit more complicated. But one thing you notice here is that this definition does require one of the factors to be a unit. So this is kind of like our definition of irreducible. Our definition doesn't have quite as much in it. For example, we don't require that irreducibles be positive, but it does have that idea that one of the factors has to be a unit. So anyway, in number theory, prime sort of means what we mean by irreducible. But we also prove in number theory, so we can prove that if P is prime and P divides AB, then P divides A or P divides B. And in fact, some textbooks refer to this as the fundamental theorem of arithmetic. Most textbooks that I know of refer to the one about every positive integer having a unique prime factorization as the fundamental theorem of arithmetic, but sometimes people use that to refer to this lemma alone, and then what we usually call the fundamental theorem is a corollary of that. But the reason I wanted to point all this out is that there's an insight that we can gain from this that's going to help us with this proof in this video. And that insight is the way that we get here, at least at some point along the way, depending on what lemmas you prove along the way, is we use something called Bézout's identity. Which says that if P and A are relatively prime, that is their GCD is 1, then there exist x and y integers such that px plus ay is equal to 1. And that ends up being key to the proof, because if you know that P divides AB and P doesn't divide A, so let's suppose that's not the case, then you're going to have to prove that P divides B. And the way you do it is you say, well, if P doesn't divide A, then P and A have to be relatively prime, since P is prime itself. And then you can say this, you can use Bézout's identity, and you can multiply everything by B and get P bx plus A by, and I'm being sort of liberal with ordering of the factors here, that equals B. And because you know that P divides this term and P divides this term, that means P has to divide B. So that's the idea of the proof in number theory. In this video, we're going to prove it for a principal ideal domain, of which the integers are an example. All right, so here's our proof. And our proof is going to use a little bit different machinery, but that's because we need to in order to account for all of the things that could happen with a principal ideal domain. All right, so let's assume D is a principal ideal domain. And just before I go on, I want to say as an aside, this is another good video where you might want to stop the video periodically and see if you can come up with the next step on your own. I'm not going to slow down because this is a video, you can pause it, but you definitely should take the opportunity to try and prove some parts of this on your own if you can. All right, so we're going to assume D is a principal ideal domain, and we're going to let P be an irreducible in D. Okay, so again, P is non-zero, and any factorization of P into two factors must involve a unit. All right, so let P be irreducible. We will show P is prime. And the way we're going to approach that is we're going to start with the definition of prime. So our definition of prime in ring theory, P prime means that if P divides AB, then P divides A, or P divides B, and P is a non-unit. Okay, we already know that P is not a unit. That's part of P being irreducible, so we need to prove the other thing. All right, so assume A and B belong to D such that P divides AB. We're going to start there. And we will also assume that P doesn't divide A. We will show P must divide B. This is a common strategy for proving a situation where you want to prove something or something else is true. Like if we want to prove P divides A or P divides B, let's just knock out one of these. Let's assume this one's not true and see if that forces this one to be true. All right, so we're going to try and show P divides B. All right, so since P doesn't divide A, and this is where the proof starts to diverge a little bit from what we do in number theory, because we haven't built any machinery around GCDs here. We could, but we're not going to right now. Since P divides A, that means A is not a member of the ideal generated by P. That's going to be key here. So A does not belong to the ideal generated by P. So let I equal the ideal generated by A and P. This is a bigger ideal because A does not belong to the ideal generated by P alone. Okay, but this bigger ideal lives inside a principal ideal domain. So since D is a PID, this means that I has to have one generator. There must be some Q in D such that I, which is the ideal generated by A and P, is also just the ideal generated by Q. So in other words, this ideal has to be principal. All right, so we're going to use that in our proof. And for those of you keeping track of how this maps to the proof that exists in number theory, the way that this works is Q functions as sort of a GCD of A and P. If you think about the integers and think about, for example, the ideal generated by, I don't know, 9 and 12, well, that's a principal ideal. It doesn't have to be generated by two different elements. You can just have it be the ideal generated by 3, and that 3 is the GCD of 9 and 12. So this is sort of our substitute for having GCDs in ring theory, at least for the time being. Now, just a note on strategy here. Keep in mind that the one thing that we know about P is that P is irreducible. So our strategy needs to be oriented towards writing P as a product of two things and then using the fact that one of those things has to be a unit. And this is where we're going to start to do that. So we know that P belongs to the ideal generated by Q, because P certainly belongs to the ideal generated by A and P, so P has to belong here. So since P belongs to the ideal generated by Q, there is some element, I'm going to call it R, some R in D such that P is equal to QR, because being in the ideal generated by Q makes you a multiple of Q. So P has to equal QR. And now at this point, aha, I've got this irreducible written as a product of two things. Now let's use that. So since P is irreducible and a non-unit, Q is a unit, or R is a unit. Let's first address the case in which R is a unit. So if R is a unit, then, well, one thing I can do is I can move that unit over to the other side of the equation. Then I have P R inverse equals Q. Okay, so P R inverse equals Q, and thus Q belongs to the ideal generated by P. Now that should seem strange to us because that means the ideal generated by Q is a subset of the ideal generated by P. Now, why is that? Well, there's two ways to see it. One way of seeing it is if Q belongs here, then every multiple of Q belongs in here. And, well, this is really just all of the multiples of Q. Other way to see it is this is defined to be the smallest ideal, or well, it's not defined to be, but we've proven it's the smallest ideal containing Q. And now this contains Q, so this is an ideal containing Q. It must be bigger than this. All right, but that creates a problem for us because now this ideal generated by Q is a subset of the ideal generated by P, and that is strictly a subset of the ideal generated by A and P. That's a proper subset because we assumed that A wasn't in this ideal, and we said that that was equal to Q. That's a contradiction. So this can't be the case. R cannot be a unit. So that leaves the other possibility, which is that Q is a unit. So Q must be a unit. All right, but then that means that 1 has to belong to the ideal generated by Q because 1 is equal to Q times something. If Q is a unit, it has a multiplicative inverse. So that belongs to the ideal generated by Q. But that ideal was equal to the ideal generated by A and P. So 1 belongs to the ideal generated by A and P. And that means that 1 can be written as 1 equals AX plus PY for some X and Y belonging to D. That's the Bezout's identity part of the proof there. So we got there by showing that this Q, which again functions as the GCD of A and P, is basically 1. If it's not 1, it's a unit, which is sort of like being 1 anyway. So that means 1 is a R combination, or sorry, a D combination of A and P. And now we're going to do the same thing that we do in the number theory proof. So back to the number theory proof. So since 1 is equal to AX plus PY, we know that B is equal to ABX plus PBY. And since P divides AB by our assumption, and P certainly divides PBY, I guess I could just go ahead and say P divides ABX as well, because P divides AB. P must divide B, and that's what we wanted. Therefore, we conclude that if P divides AB, then either P divides A or P divides B. If P doesn't divide A, then it ends up having to divide B after all of this reasoning. So anyway, that's the proof. So now we know that if we are in a principal ideal domain, every irreducible must be prime. And that's going to be important because the next thing we're going to do is we're going to try and show that in a principal ideal domain, every non-zero element has a unique factorization into irreducibles up to associates and ordering of the irreducibles. And key to proving that is going to be knowing that irreducibles are prime. That is, if I see an irreducible somewhere in a product, that irreducible has to divide some factor of the product. Stay tuned for more.